for inviting me to give a talk this afternoon. It's a great shame we can't all be together in person, but this is the next best thing. So thank you again for inviting me. I'm going to talk about something a little bit different. I guess a number of you know that for a long period of time I worked on various different types of energy harvesting, and I still do a little bit of work on energy harvesting. My early work was largely on motion-driven energy harvesting devices and the electronics to exploit the transducer in an optimal way. Since then, I've started moving on to looking at an alternative solution to the application areas that energy harvesting is typically deployed. So essentially, what I'm going to talk to you about this afternoon is the sort of basic premise that sensor networks are discussed a lot. They are now being deployed to some extent, but there's a lot of discussion in the literature about sensor networks and some elements of this in terms of industrial deployment. Reliability and power supply issues are still an issue in harsh environments. And energy harvesting is going some way to resolving this, and the idea of implementing things like mesh networks for communication is trying to reduce power consumption. So there's a good body of work that has been done already that tries to displace or augment batteries and the restrictions that come with batteries. The issue, though, sometimes is that whilst energy harvesting can be very useful for solving some of the scenarios where we want to deploy sensor networks, because the power that you can generate with energy harvesting is generally relatively low, the devices are small. If we're talking about ambient motion, in many scenarios, the driving motion is quite limited in terms of the energy we can pull from that vibration, very frequency dependent, as you all know. So there are certainly applications within the IoT where energy harvesting is going to struggle to provide what we need it to provide. And so what I want to look at today is an alternative to that, which is wireless power transfer. And you might sort of initially think, well, how does wireless power transfer fit in to an Internet of Things wireless sensor network type of application? Because you think perhaps immediately of wireless power transfer as being associated with your electric toothbrush, perhaps charging an electric vehicle. And you first of all probably think the power levels involved are therefore much higher than typically you would see in a wireless sensor network and what an energy harvester is trying to solve. And also, it's not obvious at first thought if you're going to use wireless power delivery for maintaining a wireless sensor network, it's not obvious that it is as convenient by any means as an energy harvester. The whole point of the energy harvester is you put it there and it works and you leave it forever and you don't have to do anything with it. If you're going to now start deploying power to devices through some wireless powering means, then the question is, how does that power actually make it to the device when that device could be embedded throughout some environment? So I want to explore that as a concept, and I've got some videos to show you around this concept. And as part of that, I'm going to take you through a bunch of the technical challenges that we had to solve effectively in order to allow wireless power transfer to play alongside energy harvesting in terms of the concept of the wireless sensor network, which is still where the bulk of the work on energy harvesting has its ultimate application. So a little bit different perhaps to what you might be used to hearing on these seminars, but I hope it'll make you think a little bit about some of the alternatives to the overall application space that we're trying to solve here. Just to give a broad overview here, the range of practical power levels that you see in different applications is immense. Look at the dynamic range of these figures here. What's that, a factor of 21 orders of magnitude here between total world electrical generation capacity and what you get on a received cell phone signal down at the nanowatt. And you can see that the wireless sensor network is listed in this table as being typically consuming around about 1 milliwatt, maybe a bit less than that, but with energy harvesting devices, we're typically talking in the microwatts to milliwatts type of range. Typically 1 milliwatt is probably very good for many energy harvesting devices. And so you start having to play tricks like duty cycling wireless sensor nodes in order to meet the average power requirements and put in something to deal with peak power requirements when you're powering these devices off energy harvesters. The wristwatch here down at 1 microwatt, it's then quite clear when you look at this table why the Seiko Kinetic watch was an excellent example of an energy harvesting enabled device, because its power consumption is low enough to enable an energy harvester to power it and its complete functionality. Of course, once you start talking about smartwatches, the power levels that are required are much, much higher. This is a slide which I think is also quite useful to set energy harvesting in context with batteries in particular. And of course, it's difficult to make an exact analogy between batteries and harvesters, because theoretically an energy harvester has got an infinite energy available if you leave it long enough, but it's limited in terms of power, whereas a battery might have a very, very high power capability, but of course it's limited in terms of energy. And so making that direct comparison is quite tricky. And so in this table, what you can see here is the power required by a device, or the power that is able to be produced by a harvester of a certain volume. And there's some assumptions here for a motion-driven harvester and a certain proof mass of the harvester and a certain acceleration. But comparing it to, in this case, a lithium battery, you can see here, if you have a device which is about 1 centimeter cubed, and we expect a battery to run for 1 month, then we could draw getting on for 1 milliwatt out of that battery if we had a 1 centimeter cube battery. If we wanted the device to run for 1 year, then clearly we're on the black dotted line there, and we would only be able to draw something like what's that, 20 microwatts for the device. So matching the energy harvester size and the battery size to the device is obviously a very important concept as well, because you can't have, you could say, well, I could potentially power my smartwatch from an energy harvesting device, but then the energy harvester would have to be, I don't know, 100 times bigger than the watch, and then it's not practical. So what is this graph is really showing you? It enables you to see why, for instance, the wristwatch is a very good application, because the amount of power needed and the volume that is available line up very nicely. Once you start talking about the wireless sensor network, where the volume for a particular node may be quite small, maybe around the same size as a wristwatch, but the power requirement is significantly higher, potentially a factor of 10 to 100 times higher, then you start to see why the wireless sensor network is a very interesting application for energy harvesters, because it's really a stretch target to try and generate enough power for an energy harvester. So what happens if harvesting isn't enough? So I hope I've sort of convinced you there that energy harvesting is, you're already convinced energy harvesting is useful, but that it isn't the solution to every application, because there may be times when the power we require is just too much. A potential solution to this, and I'm going to play you a video in a second, and I think once you see the video, you'll just understand exactly what we're going to address in this seminar. Something that we call the synthetic sensor network, or Synthsense for short. And the basic concept of this is to provide autonomous power delivery into a wireless sensor network. And if you provide autonomous power delivery, then you want to have some device which is hauling power around, literally carrying the energy around the network, and is able to then transfer that energy from the carrier device to the receiver device. And the receive devices are the nodes in the IoT network, and the carrier device in this case that is actually physically moving the energy store around the network is a drone. And I'll show you now a video. I hope that's playing okay over the WebEx connection. But here's the concept. We've got a drone here with an induction coil mounted on the front of it, and that drone can fly around a sensor network deployment, shown here as being something like an oil pipeline. It's able to then inject some power into those sensor nodes, and it's able also at the same time, while it's doing that, to collect some data from those sensor nodes if that's an important thing to do. So that's the basic concept. Can we replace these sensor nodes from being constrained by the limited power that energy harvesting could provide. And we could perhaps have a dual solution here, energy harvesting to provide a backup power, and then perhaps every so often, if we want the device to be able to do more power intensive things, like it needs to take some video, it needs to actuate something, we can fly along with the drone, sorry. We can fly along with the drone, and we can top up the energy reservoir in the sensor network itself. So hopefully wireless power may be a solution to this. You can appreciate why I'm talking about wireless power in this context, because if we try and make physical contact with those sensors in order to try and make the recharging of the sensor, it's going to be very difficult to land the drone accurately enough in order to transfer power. And in addition, that sensor may be buried in the infrastructure, it may be buried underground, maybe embedded into a wall. It may not be possible to make physical contact, but it may be possible to do wireless power delivery in this sense. So just to give you a sort of indication as to what people have demonstrated in terms of distance for wireless power delivery using an inductive type system, this is a photograph that came out of some work in MIT by well, the team here led by Marin Sulacic, who's the guy sat in the middle there, and you can see they've got two copper coils here. They're just mounted on some what looks like polystyrene as an insulating material, and they're able to light a light bulb over a couple of meters distance here from coils that are really certainly a lot less than a couple of meters in diameter. They're probably something like 50 centimeters in diameter, and they're doing about 4 coil diameters of distance between the transmitter and the receiver. And they're certainly not the first people to work on wireless power by any means, but this was a picture that certainly got me interested in the topic. I thought it looked quite magical as a thing to see when you've got these people here standing in the middle of this wireless power delivery system, and they're transferring power over such a long distance. Now I look at that picture, of course, that I've done a good amount of work on wireless power, and I start to wonder about the magnetic and electric field strengths that the team is exposing itself to for the purposes of that photograph. So what am I going to cover? I want to talk about the challenges of adapting a wireless power transmission for the wireless sensor network. I'm going to talk here a little bit about the basics of wireless power, because I'm sure most of you will perhaps have some vague idea as to the operation of this, but the background for most of you is in energy harvesting and MEMS devices. So I'm going to try and tell you a little bit about some of the constraints and some of the solutions to providing wireless power delivery inductively over a relatively long range. I'll go through that in terms of the magnetic link and the way that we have designed the transmit and receive electronics. And then I'm going to finish by showing you a little bit about the actual concept that I just mentioned there, Synthsense, and some of the deployments that we've started to do and some of the testing that we've been doing on wireless power transfer with drones. So let's start by looking a little bit at wireless power delivery. I have another video to show you here where we kind of got the idea initially for how do you power a sensor network using inductive power transfer. I hope this video is going to play. This is a very large induction coil that we built. You can see on the left there, a 2-turn coil made out of copper pipe, and what is here a relatively large receiver on that plastic former there with quite a few turns on it, some receive electronics, and you can see here that we are charging a battery over several meters there. And the idea was that if you were able to put a magnetic field generator into an environment, you would then potentially be able to put multiple sensors within that environment and to be able to power them. So it's an attempt at doing a relatively long range IPT system. So IPT is inductive power transfer. Because it's inductive, it works in the near field. Consequently, it tends to be always limited to fairly short range devices. So when I'm talking about long range here, I'm typically talking about more than 1 coil diameter for the transmitter. And a lot of these systems, you can see that one there is over 1 meter coil diameter for the transmitter. Some of the systems are significantly less because they're constrained. So when we fit an induction charging system onto a drone, it's typically going to have to be a lot less than a meter in size in order to physically fit it onto the drone. What is it that makes that difficult? We want to try and achieve a flexible charging type of solution here. And in the scenario I've described, this Synthsense scenario, where we want to fly a drone around and recharge a bunch of sensor nodes, then the alignment between the transmitter and the receiver is absolutely crucial with regards to specifying the system. And the point is, you can't guarantee alignment between the transmitter and the receiver. You only know roughly where the receiver is. You know, of course, from the drone perspective, you know exactly where the transmitter is. But if you have to hover next to something in order to charge it, or if you have to land in order to be able to charge something, you can't guarantee landing in exactly the same place every time. If you're hovering next to something, then there'll be a natural amount of motion between the transmitter and the receiver as you're doing the charging. And so what does that mean for the wireless power system? It means inherently it has to be able to cope with a certain amount of change in the geometry of the magnetic link. So it has to have, in that sense, some sort of dynamic system capability where there is dynamics there in terms of the physical positioning between the transmitter and the receiver. So that means essentially I've got to have that tolerance to misalignment. I've got to be able to cope with the system changing its geometry during operation. I want the system to be high efficiency. And if I'm going to start attaching this type of system onto a drone, I need it to be very lightweight as well. So there are some commercial solutions that are out there with regards to inductive power transfer. The electric toothbrush I mentioned earlier is something that you're probably quite familiar with. There's also the Qi charging for mobile phones. I think it's something that is available, for instance, on quite a lot of Samsung devices, but also many other devices as well. And the thing that the Qi devices and the toothbrush have in common is that you typically have to get the transmitter and receiver pretty well in contact with each other for the device to actually charge. So the toothbrush sits on top of a little cradle in order to charge itself. The phone gets placed onto the Qi charging mat that you can see on the left of this slide. And so there's no electrical contact between the toothbrush and the charger, or the phone and the Qi charging pad, but there's physical contact because you just rest one on top of the other. And you can then potentially guide quite exactly the positioning between the transmitter and the receiver. What we need to do in order to enable this Synthsense concept is to have a greater standoff between the transmitter and the receiver and allow for motion between the two while the charging is occurring. Now, something that gets a little bit closer to that is the sort of system that is being proposed for an electric vehicle charger, and you can see an example of that in the middle of the slide there. So there's a greater air gap between the transmit pad and the receive pad, but something that all of these devices have in common is they tend to be quite heavy. And the reason that they're heavy is that the approach to the design of the system is basically relying on trying to maximize the coupling factor between the devices. And I want to talk a little bit now about why that's important and alternative approaches to maximize the coupling between the devices in order to still maintain high efficiency of getting energy across that air gap. So our approach to building the wireless link here is rather different from this approach to put lots of ferrite material into the coils and to maximize the coupling factor. You can see here an animation of a test rig of ours just in the lab here, where we're moving a transmit coil and a receive coil with respect to each other in order to characterize a system, allowing for significant misalignment between the transmitter and the receiver. So let me tell you a little bit just about the basics here of wireless power transmission by an inductive means. The efficiency of the magnetic link is of key importance for all of the reasons that efficiency is normally important. We don't want to waste energy. We don't want to generate heat, because if we generate heat, we have to dissipate the heat somewhere. That requires heat sinks. And particularly within the Synthsense concept, where I'm flying a drone around to different sensors, what I don't want to do is to waste a lot of that energy that I'm carrying around by dissipating it in heat in a sensor. I'd like to make sure, because I've only got a finite energy that I can carry with me, I'd like to make sure that absolutely as much of that as possible ends up in the receiver. And so the formula here that determines the efficiency of the magnetic link is this formula here, k squared q1 q2 divided by 1 plus square root of 1 plus k squared q1 q2 squared. K here is the coupling factor between the transmitter and the receiver. That's the fraction of magnetic flux produced by the transmitter that is intercepted by the receiver. And Q1 and Q2 are the quality factors of the transmit and receive coils respectively. So this is where the type of design for this system starts to differ very significantly from a transformer. So a transformer is the sort of closest normal electrical component that you'll be familiar with. And of course, that transfers energy from primary to secondary through a magnetic field, rather than having a direct conductive contact between the primary and the secondary. But it does it in such a way as to wind the coils on a common core for the transformer. Consequently, the value of K is extremely high for a transformer. K might be 99% or 0.99 in this formula. Once we start to look at an inductive power transfer system where we need significant distance between the transmitter and the receiver, the coupling factor is going to drop to typically sub 10%. Depends very much on the distance between the coils. It depends on what magnetic materials you might try and attach to the system in order to improve the coupling factor between the coils. But essentially, you can see here that if you make this product k squared q1 q2 higher and higher, you get a higher efficiency. So the key thing here is a lot of people, when they design wireless power systems, of course they want the Q factor to be high because that will maximize their k squared q1 q2 product. But they also try very hard to push up K in order to move themselves as far to the right on that graph and get the link efficiency as close to 1 as possible. So you can see here, as long as you've got a k squared q1 q2 above 350, then you can have a link efficiency of about 90%. If you work on trying to increase K, typically, as I've said, you do that by putting a lot of ferrite material into the coils to try and shape the flux and improve the flux linkage between the transmitter and the receiver. What you tend to do then is potentially, to some extent, compromise the Q factor, or at least you're not concentrating. You're not designing for maximum Q. You're designing for maximum K, and then once you've done that, you're trying to then make the Q as high as possible. An alternative approach is to say, if I need to have the greatest freedom of movement possible between transmitter and receiver, I need to accept that the coupling factor is going to be low. And if I'm going to have a low coupling factor, which is inherent in getting a big distance and a big tolerance to misalignment between the coils, then I need to really go all out in maximizing the Q factors. Because if I can get, if I can double the Q factors, then I can halve the value of K. So I can get significantly larger range between transmitter and receiver. So the question then is, how do I make the highest Q resonators possible? And well, this ultimately comes down to what Q factor can you achieve for your inductors on the primary and the secondary. Typically, the Q factor is going to be limited by the Q of the inductors. They will typically be in a resonant tank with a capacitor. Q of the capacitor is probably going to be significantly higher than the Q of the inductor, just because we can make very, very high Q capacitors. We can only make moderately high Q inductors. And you remember that the Q factor of an inductor is just is proportional to omega. It's omega L over R. R we try and minimize here so we try and make the coils quite nice and fat to give them a big surface area. And consequently, we have to push up omega. If we push up omega, we push up the Q factor of the coil. Now that's true to the extent that that we don't start to radiate from the coil. Eventually that coil will not look like an inductor if we drive the frequency too high. It will start to look like an antenna, and it will start radiating energy into the far field. So we want to avoid that. We're trying to do a near field system here that is coupling energy only using the magnetic field. And of course, the resistance of the coil goes up because of skin effect. So the omega L over R, it's not fair to say that doubling omega will double the Q factor, because it will also push up the resistance at the same time. However, there is an optimal point here of operation just before the radiation starts to kick in, where you've maximized the Q factor of a coil. Now, for the sorts of coil sizes we're talking about here that are typically 10 to 30 centimeters in diameter, then it so happens that the optimum frequency of operation to maximize the Q factor comes out in the low megahertz region. That then means that if I'm going to operate the device in low megahertz, I need to be able to drive, and that will optimize the efficiency of the link. Then I need to be able to build electronics on the front end of the link to drive the link at that frequency, and on the receiving end of the link in order to be able to receive power at that frequency and do all of that nice and efficiently. And that is something that is not as easy as perhaps it sounds at first. But if you've got any experience of working on power electronics, either perhaps on things like motor drives traditionally, or switch mode power supplies, then you'll be well aware that if you keep increasing the frequency of operation of a piece of power electronics, then the switching losses will increase. So every time we turn a transistor off or we turn a transistor on, there's a blip of energy loss that occurs in the device, because voltage and current will be high in the device at the same time. As we push into megahertz operation, that problem becomes very, very significant. And this is one of the reasons why a lot of power electronic systems, be it motor drives, power supplies for your laptop, etc., they tend to work in the 100 kilohertz type of range. And as I push up in frequency, the losses due to that switching tend to become problematic. There is a way around this, and the way around it is to use a soft switching type of converter. And a very common soft switched inverter is this one. This is a Class E inverter. If you come from a radio frequency background, you would typically know this circuit as a Class E amplifier. And the basic operation of this circuit here is that you put a square wave into the gate of the MOSFET Q1, and that will generate a sine wave current flowing in C2, L2, and RL here at the same frequency as the gating of Q1. L2 here is the inductance of the transmit coil, and RL is the reflected load. So the energy that is dissipated in RL is modeling the power that is taken from the transmit side across the air gap to the secondary side, and so it looks like a power dissipation in the transmit circuitry, so it's represented here as a resistor. This circuit is what we call soft switched, because the resonant action forcing the voltages across the drain of the MOSFET here, as shown by the red curve in that plot, you can see that you get a resonant pulse of voltage across that MOSFET. And so when the voltage is at 0, it's a good time to turn the MOSFET off. And then you get that resonant pulse across the MOSFET. It naturally comes down to 0 again, and that's a good time to turn the MOSFET on. So if I can ensure that I turn the MOSFET off and on, whilst the voltage across it is 0 or very nearly 0, then my switching loss is very, very low indeed, and I can achieve very high efficiency power electronics even at megahertz. And remember, that's the prerequisite for getting the high capability in the magnetic link that gives us the freedom of movement between transmitter and receiver, which is absolutely fundamental to this application where we might want to recharge a sensor network wirelessly through the action of a drone. The difficulty, of course, is that these resonant circuits, and anything resonant, and this is true, of course, within any motion-driven energy harvester that you build, it's very sensitive to different parameters. If you change the temperature slightly, the resonant frequency may change. If you change the load on the energy harvester, you may pull down its resonant frequency. And so the constraints here on meeting that 0 voltage switching to maintain the high efficiency for this Class E type of circuit mean that actually there is only one operating point where it works properly. That's the one that's shown on the left here. You can see the MOSFET being turned on and off by the signal at the bottom, and you can see the voltage across the device increasing and decreasing. And when it decreases to 0, that's a good opportunity to turn the MOSFET on at 0 loss. If my reflected load, however, and remember the reflected load in this circuit is RL here, that's the power, that's representing the power taken out of the transmitter into the receiver. And that depends, of course, on the power consumption of the receiver. And of course, it also depends on the distance between the transmitter and the receiver. So if I change the distance between the transmitter and the receiver for a given value of load on the receive side, then that reflected load value will change. So it changes because of changes in different parameters. And if RL does change, either because the geometry of the link has changed, because in this case, the drone is hovering close to a sensor, but it's not in a stationary position, there's a little bit of continual movement, or because the battery in the sensor is nearly charged and therefore its effective resistance looks higher as I'm trying to charge it, then I'll start reflecting back a non-optimal load onto the inverter. And you can see on the right-hand side there where the resistor is less than the optimal value in the middle, and on the right-hand side where the reflected resistance is higher than the optimum value. And in the middle case there, the drain body diode of the MOSFET comes into conduction, and in the right-hand case, we have to switch the transistor off whilst there's still, switch it on whilst there's still voltage across it. And so any capacitance associated with that transistor immediately gets discharged into the transistor itself and significantly increases the switching loss. And if we're going to develop a really useful wireless power system for the Synthsense application, or indeed for many other applications, we have to be able to cope with not having perfect alignment between transmitter and receiver. And ideally, the system needs to operate dynamically where there's continual movement between the two, but it certainly needs to operate where a drone could land in one place one time and another place in another time, and it doesn't detune the electronics. Our solution to that is to add an additional resonant branch into that circuit. So the circuit you see here in the top right of this slide is what we call a load independent class EF inverter. So it's taking the class E inverter that you saw, which maintains soft switching only for one operating point, and the addition of this second network here, C2 and L2, allows you to sufficient degrees of freedom when designing the circuit here, so that the system is now tolerant to changes in RL. So what that means is I can now have a transmitter, I can move that transmitter close to a receiver and further away from a receiver. And as I do that, the inverter will still maintain soft switching and maintain high efficiency, even as I get that movement between the transmitter and the receiver. And you can see some plots of this equivalent to the plots that we looked at before for the class E inverter, that for a nominal value of reflected load, I can turn the device on when the voltage across it just goes to 0. And you can see as I then change the value of RL, either decrease it or increase it, I still maintain this 0 voltage switching, so I don't incur any switching loss. You'll notice that the trajectory of the voltage across the MOSFET between the time that it gets switched off to the time that it gets switched on is different for each of those three scenarios. Different reflected resistances, different voltage trajectory across the MOSFET. But crucially, the start and end point are exactly the same, even if the trajectory is different. You can see an example of that on this slide here, where it's a capture from the oscilloscope, where the device is actually, the setup here is that we've got a fixed transmitter and a receiver that is held in someone's hand, and they're bringing the receiver up to the transmitter and taking it away again, bringing it up and taking it away again. And the yellow here shows you the voltage across the MOSFET of the transistor. And you can see that in all cases, it maintains that 0 voltage switching. An alternative, or rather an additional benefit of this circuit, the green trace here shows you the current in the transmit coil. And one of the additional constraints we place on the design of this circuit is to try and make the current in the transmit coil as constant as possible, independent of the position of the receiver. And the reason I do that is to decouple the behavior of the transmitter from the receiver. So my objective is to have a very efficient, constant current generator at megahertz frequencies. So I'm generating a constant magnetic field, and I can bring a receiver up to that and take it away again, and I can transfer power into that receiver without disturbing the proper operation of the transmitter. So that, in almost every case now, is the approach that my group takes to the design of the constant current magnetic field generation for the transmitter for an inductive power transfer system. Incidentally, one additional benefit from maintaining that constant current in the transmitter here, or very nearly constant current in the transmitter, is that it allows you to then fairly effortlessly charge multiple devices from the same transmitter. So because one receiver is not disturbing the field that is being generated by the transmitter, I can bring a second device up and charge that at the same time. And then I have a pretty good degree of decoupling between those two receive devices. So what do we do on the receive side? Let me tell you a little bit about the work we've done on the receive electronics. As I mentioned, the circuits here that couple into the magnetic link all tend to be resonant. You've seen the resonant circuit there for the transmit side, and the receive side also is resonant. The reason that I want to add resonance to the system primarily is that I've got an inductance to drive for the magnetic link, and I need to drive therefore a lot of volt amps in that coil, and I don't want to have to rate the electronics to the same VA rating. VA rating is what we have to pay for any piece of power electronics. If you push the voltage up, you pay for it in more and more expensive silicon. If you push the current up, again, you have to put more silicon in, and it increases the cost. What we do here by adding this resonance, and you can see a series resonance here on the secondary CS and LS, that is cancelling some of the voltage that appears therefore across LS, and it is allowing me in this case to reduce the VA rating of the active electronics for the rectifier that is present on here, and it allows me to tune out the inductance of the secondary so that the reflected impedance back to the primary is just RL. What I don't want to do is to reflect back reactance to the primary side circuit. And let me just go back a couple of slides just to reinforce that. With this class EF circuit here, what I can allow for is changes in RL, but I can't make R a generic impedance, because if I put some reactance into there, it will detune the circuit. So what I've managed to do here is to design a circuit such that that resistance can be changed, but it has, one of the constraints is it has to stay resistive. So if I reflect back something other than a pure resistance, I'll still detune the circuit. So I have to therefore cancel out LS with a CS in order for that to happen, and it also then reduces the VA rating that I see on the active electronics on the receive side, and the same goes for the primary side. So if I put a series resonance here on the system, then I can see that it's possible for me to reflect a perfect resistance here back to the primary side. If you use a parallel resonance on the receiver, which some people do, then you don't have an exact reflection back to the primary of a perfectly resistive load on the primary with a parallel tuned circuit on the receiver. It's true for a series, but it's not true for a parallel. So we tend to use, it's only true at one point. So here we try and obviously allow for changes in RL. We can allow that to happen if we have a series resonance on the receiver and we set the parameters up properly. And in this system now, I can change the value of RL on the receiver, or I can change K by moving the coils further apart with each other, and the circuit that is then powering the transmit coil will operate properly as per the animations that I showed you earlier. It'll maintain a high efficiency, it'll maintain a constant current in LP, and it'll therefore allow me to pull power into the receiver by actively changing the value of RL on the receiver, which I can do with an additional power conversion stage. So for this type of application where I want to take a drone up to a receiver, squirt some power into the receiver as quickly as possible, and fly the drone away so it can go and recharge the next receiver, I typically have to have a supercapacitor type of arrangement in the receiver to allow me to get that energy in there as quickly as possible. So I have a receive coil, I have a rectifier, I'll typically then have an interface to a supercapacitor, and then I'll have quite a varying voltage on that supercapacitor. So I have to have some sort of additional piece of power electronics then that powers the load and regulates the change in voltage from the supercapacitor as it's being charged and discharging to give me a constant voltage across the load. There are various things that we would like to do with that receiver apart from purely maintaining a voltage, a known voltage on the load. And the most important thing here that links this with the operation of the transmit circuit that I showed you is to try and make sure we present a pure resistance. So clearly in the situation here with a series tuned receiver, and as long as it's tuned properly, I can change the value of RL, and that will change the value of RF, the reflected resistance. That's true in this scenario where I've got a simple RLC circuit on the receiver. Of course, in reality, the receiver is not going to just have an RL. RL is going to be replaced with a high frequency rectifier, some power electronics, a capacitor, plus the load electronics for the sensor. So what I need to try and do here is to make sure that that rectifier interface that attaches to the coil resonator presents a purely resistive load back to the transmit side. In other words, it also has to have a purely resistive input impedance, can't have a reactive input impedance. If the rectifier has a reactive input impedance here, it will reflect some residual reactance back onto the transmitter, and that will detune the transmitter, and we don't want that to happen. We then need this supercapacitor based interface. As I said, we want to be able to ideally charge in a few seconds. If we can charge the device in a few seconds, we can fly the drone up to a device, charge it, and fly away again. And then, as I said, we want to have something that allows us to regulate the voltage as presented to the load. We've looked at various different solutions here for the receive electronics. You can see a couple of options here. The rectifier in the bottom right of this slide is the standard full wave rectifier that you'll be familiar with. There's a half wave rectifier at the top there. These are current driven, by the way, rather than being voltage source driven, because if you think about the series tuned receiver, I'll go back a couple of slides again. For a series tuned receiver here, look at the figure A on that diagram. You've got an inductance in series with a capacitance. That inductor is going to force current to flow in that circuit no matter what, and hence I can't immediately open the circuit without causing a problem. There's some inertia in that circuit because of LS, and consequently I treat the rectifier that's attached to this circuit as a current source driven rectifier rather than the voltage source driven rectifier. So what you see in the top right of that slide is a half wave rectifier intended to be driven from a current source. These are so-called Class D. You would know them as a standard rectifier, but they're what are typically called Class D rectifiers, because of course there are also Class E rectifiers and Class EF rectifiers. They're fairly simple. They have a low component count, but they have a problem here with parasitics in the components. When we start designing these systems, the realities of making a diode, for instance, and the parasitic junction capacitance of the diode will detune the magnetic link if we're not careful. So we have to take that into account in the design. That's a significant problem often in the use of this type of simple rectifier. What we've done is to introduce a hybrid, we call the hybrid Class E rectifier, this device at the bottom here. It's a hybrid because it now includes some element of parallel and series tuning of the coil. You can see a CS and CP. The reason for that is that it allows us to manipulate, it's an impedance transformation. I mean, it's an AC potential divider, but we're using it here as an impedance transformation so that we can then make sure we map back onto the primary an optimal value of reflected load. As I mentioned, if I go back a few slides again, this reflected load that is seen by the receiver here, there are different values of reflected load that the receiver is able to cope with. Only one of them will give you the maximum efficiency of the magnetic link. So whilst it's possible to cope with different values of R, there's still a value of R that you'd like to aim for, which is the one that gives you the best efficiency of the magnetic link. And so by putting in this additional capacitive divider here, again, we get an extra degree of freedom from impedance transformations. We can reflect back an optimal load onto the transmit side circuitry here, and thus loading the link in an optimal way to maximize the efficiency. There's then a whole bunch of additional bits of circuitry, as I mentioned, that have to glue this together, charging a supercapacitor and putting here a suitable post-power conversion stage on. Luckily, at this point, if the rectifier is properly designed, the rest of the interface circuitry can be made up of what is largely off-the-shelf standardized bits of power electronic design. So let me talk a little bit more now about the application and some of the testing that we've been doing, and I've got a few more videos to show you here as well. So the concept, as you've seen, is that this UAV, this drone, is going to be able to visit multiple sensor devices within an embedded sensor network. In between visits, the sensor is going to be accumulating data. It's hopefully got very low power requirements, but every so often the drone can come along and it can inject power into the sensor node via the systems that I've just described, that allows it to do it relatively quickly. It allows it to hover. It allows motion between the transmitter and receiver while it's charging because of the design of the electronics. And then also the drone can lift the data off the device at the same time and fly that around and fly it back to a base station. So the basic concept, I called it at the beginning. I said we called it a synthetic sensor network, or Synthsense for short. The name actually is inspired by synthetic aperture radar, where you get effectively a larger effective aperture of a radar by being able to take radar scans as you move the position of the radar dish itself. So you mount it on an aeroplane, you can fly it around. You get effectively a more sensitive radar by having a movable dish in this case. We've got a similar sort of concept here, that we're flying something around in order to collect data and to increase the longevity of the system. Hence, we took inspiration from synthetic aperture radar for the naming of this type of wireless sensor network. So again, you're now very familiar with this concept. Drone flies up, squirts some energy inductively at the receivers, and also gathers some energy, gathers data back from the receiver, from the embedded wireless sensor node. We did a test deployment here at Imperial. Since we did this, the rules for operating drones on campus have changed somewhat. We wouldn't be allowed to do this anymore, I think. But you can see here sensor nodes put on the grass here. The drone is able to fly around. It's able to land on top of a drone. And could I just ask everybody to mute if they're not? Hamid, could you mute your microphone? Thank you. So we're able to fly this drone around, we're able to land it close to a sensor, and we're able to exchange data. So we did some work where we had this test deployment in college. We built a comms link on the embedded node and on the drone, and we were able to fly that drone around the Queen's Lawn here at Imperial. I know some of you have visited Imperial, so you're perhaps familiar with the Queen's Tower here on this top-down view that you can see. We put 3 sensors on the lawn, we flew them around, and as you can see on the left there, we were able to leave them deployed for a while and then go and gather the data. The other aspect of this then, of course, is to be able to do the power delivery. So I've talked to you quite a lot about some of the theory for the power delivery here. I can show you some examples of that power delivery actually working in this case. And this is a little example that we built when we were first trying to characterize our inductive links and show that they had really good tolerance to misalignment between the transmitter and the receiver. So this is a drone here that is flying in a magnetic field. There's no battery on the drone. There's a small capacitor on the drone, but it would only enable the drone to fly for, I don't know, 10 to 100 milliseconds. So the actual power that is used here for flying the drone is being transmitted in real time from the transmit pad here to the drone itself. Just before I start the video playing, you can see the transmit pad here, the little plastic plate there with the Imperial College London logo on it. If you look at it carefully, you can just see a couple of rings. So behind that plastic plate, there's a PCB with simply a 2-turn PCB coil, which is our magnetic field generator. And then on the drone itself, you should be able to see the propeller guard ring of the drone has been copper plated, and therefore we have a single turn receive coil. Again, you can see here for lightweightness, both on the transmit side and the receive side, Part of the requirements for lightweight means that you have a very low number of turns on the transmitter and the receiver. Again, that is the thing that is sort of driving you to higher frequency. I've got to be able to drive a very low inductance coil, and so in order to be able to do that, I have to push the frequency of operation up. Let's just try and play this video. You can see now the drone propellers start spinning, the drone lifts off. It's tethered to the transmit pad here via a piece of nylon. I assure you that's non-conductive. All of the energy transfer here between the charging pad and the drone is done here via the magnetic field. And you can see very significant changes are available here between the positioning of the drone and the positioning of the charging pad, which is what we're looking for in terms of practical deployments of these systems. You could see there, I'll just play that again so you can see it. You can see the oscilloscope in the background in a second, and you can see those voltages changing in real time on the transmitter as the drone changes position relative, there you go, the yellow voltage. And you can see that the trajectory of the voltage changes as the drone changes position, but the starting and end points are the same, maintaining that zero voltage switching and maintaining therefore the efficiency of the coil driving circuit. Okay, once we'd done that, we then thought, well, this Synthsense concept has got to ultimately have the transmitter connected to a drone. So we have a larger drone here, and we have to be able to then charge a sensor device. So this is our first go at a drone with an induction coil mounted to the drone now, powered off the drone's battery, charging a sensor in the environment. The environment here is our seminar room. And you can see here the drone gets close to the sensor, and in this case it's very close. It doesn't need to be this close. This is pilot capability restrictions. And you can see here that we charge that sensor node, and the drone can then fly away. Once it's charged it's injected very quickly some energy into the supercapacitor on that receiving node, and it's able to then fly away. And for some period of time, that sensor node is then able to be completely autonomous. We then decided, and this isn't necessarily directly relevant to the wireless sensor network application, but we then thought, what if we could have a drone charging another drone? And this was us really just having a bit of fun and seeing what we could do. But what you're about to see now is the large drone is going to inductively charge a small drone, and it's going to put enough energy into that drone in just a couple of seconds to give that small drone sufficient capability to take off and to fly. So it's all being manually flown. It would be probably a lot better if we had some autonomy on the control of the drone. But you can see there, we've inductively charged the little drone. And then that drone, even in that short space of time, has had sufficient energy for it to fly away. Again, not necessarily a specific application for a drone charging a drone, but it was a bit of fun and a good capability demonstrator. We did also try and do what we were calling mid-air refueling of the drone, where we tried to fly the little drone close to the larger drone in order to refuel it in mid-air. Unfortunately, that tended to result in the little drone getting caught in the propellers of the big drone and being shredded to pieces. So that should go on one of my sort of outtake videos at some point. Okay, a final thing that we need to be able to do then is to make complete autonomy for the big drone itself. So there's a whole load of work that needs to happen here in terms of localization and having the drone automatically find the sensor. But if this system is going to work completely autonomously for a long period of time, the drone itself, the large drone, ultimately needs to be able to recharge itself. So this is a fairly recent piece of work that we did, where we fitted, we built a proper charging pad. We did this in conjunction with Thales. And we took our large drone here. We've got a better induction coil integrated onto it. We've got a charging pad here. That drone is now able to land itself. Well, it's not landing itself, actually. It's again got a manual pilot, but it's able to land on an induction pad there. Again, there's quite a big freedom for misalignment between the transmitter and the receiver here, but the drone in this case is now the receiver, and it's able to recharge itself and fly away again. This part of it is going to require the drone to be stationary on the charging pad for a longer period of time, because now we have to worry about charging a battery, and it's difficult to charge a battery in a few seconds. Of course, you probably need to be charging that battery over something like half an hour to an hour. So the drone that is maintaining the sensor network is going to recharge itself. Once it's done that, it can then fly around. It can use the same induction coil now to be able to recharge the sensors. So that's bringing me towards the end of the talk. Sort of the focus on this really was to try and make you think a little bit about what we're doing with energy harvesting devices and what some of the alternatives might be. It's very easy, I think, to sort of immediately go down the track that we don't want to have batteries or at least we don't want to be reliant on the finite energy storing batteries for powering embedded devices and wireless sensor networks. And so the typical go-to solution is to look for an energy harvesting device for a particular scenario. And as I've said, that may well be a possibility in lots of scenarios, but it may not be a possibility in many other scenarios, particularly where the power requirements on the receiver may be significantly higher. And in that sense, we think about the synthetic sensor network, where we're able to have a drone which flies around, maintains the power in the sensor network, and also can be used to haul data from the wireless sensor network and bring it back to base. The drone can then completely automate itself. It could be flown autonomously, it could find the sensors autonomously, and it can then recharge itself autonomously. So we haven't done the complete end-to-end system here. We would like to get to the point soon where we have a complete system that is fully autonomous. We can deploy a sensor, we can fly a drone around in an automated way, charge the sensors and charge the drone autonomously, but we're probably still a few months away from truly achieving that. In terms of what that means from a power perspective, if we can charge at 50 watts, and we can certainly put 50 watts into a supercapacitor on the receive node, and the sensor node power consumption is around 1 milliwatt, that's a charging duty cycle required of 0.002%, or for every hour of operation, we have to spend 7 seconds recharging the node. So it certainly seems reasonable that you would supply power to the sensor node for a minute or so, or a couple of minutes, and then the node could be autonomous for a day or longer. Quite a lot of background work has gone into obviously the material for this presentation, so thank you to all of my collaborators in the work that we've done here, and thanks to everybody here for listening. Thank you very much.
Thank you very much, Paul.